And welcome back. And today we are going to finally finish the fundamental theorem of classical potential theory. And since it says fundamental, it must be important. So that was what we've been building up to for these last 4 videos. I think I'll start with a little technical proposition. We have a compact set in C with positive capacity. And we have sigma is a probability measure. Then we can basically, well, we know using the Fubini-Tonelli theorem, we can switch the order. So we can say the integral of u sigma of z d mu e z is the same as if we do the opposite order, the integral of u to the mu e d sigma of z. And the reason for this is that these are both inherently integrals. This really is saying it's a double integral of the log 1 over z minus t of d sigma t d mu e of z. And this one is double integral of the log, same thing, of d mu t followed by d sigma of z. And so it's not automatic that you can switch integrals like that, but the fact that these are both probability measures, meaning they're finite, and that the integrals themselves are finite, that is going to allow us to do that. So knowing that fact, we can then make a statement. Mu E is the equilibrium measure. So we could say that for a given z, or for a given, sorry, let me say this, let me just write this out. That the infimum of the potential with respect to this sigma measure is some constant m. So we can say the integral of m d mu of e of z is equal to m. We're integrating a constant across a measure, a probability measure, so the total measure is 1, so we just get that constant, which would be less than or equal to the integral of u sigma z d mu e of z. So all I'm saying here is that the minimum value is less than or equal to the integral over the whole space. In addition, we have that u mu e of z, the potential with respect to the equilibrium measure, is less than or equal to the Robin constant. That's Frostman's theorem tells us that. So the integral of u mu e of z d sigma z would be less than or equal to the integral of the Robin constant. So see, we're just stating a function, one function is bounded above by something, so its integral is bounded above by the integral of that something. D sigma z, which is the Robin constant again. All right, so sorry. So what we come up with is this infimum here is less than or equal to the Robin constant. Goes there, to there, to this equality here. Or yeah. Yeah. And that last part wasn't equality, but that's where we come up with, yeah, this becomes this, which then goes to here. So what we got there is that then clear the board to give you the bottom line here, the infimum across Z and E of the potential with respect to any specific measure is less than or equal to the Robin constant, which, as we said, is the same thing as log of 1 over the capacity. So the potential as a bound, the infimum of the potential with respect to this arbitrary probability measure sigma, at any point, it's not more than the Robin constant. It could be less, it could be equal. It's pretty similar to Frostman's theorem. It's just using an arbitrary measure this time. Okay, so that's just a little technical piece we'll probably need to bring up a little later. So let's return to the Chebyshev world. So we're going to define T sub n of E to be the norm Tn of E. So remind us what this means. This capital Tn is a polynomial. It is the polynomial with the smallest Chebyshev norm, the smallest maximal error. What is that smallest maximal error? That's little Tn. So these things are all in R plus because they're norms. A norm could be 0, but the 0 polynomial is not monic, so we could not actually achieve 0 in this case because we said our polynomials are monic, so therefore if it's not the 0 polynomial, then its norm is not 0. So what this Tn is a real valued sequence. Now let's look at Tn E here. Well, another way of saying it, it's the minimum across all polynomials in Pn that are monic of the norm of P Z E. Or we could state it as the minimum across polynomials in P n minus 1 without the monic restriction of Z plus P of Z. So this is just peel off the leading term, and then we have a new P. Now, okay. And we're taking it as a given, by the way, that E is an infinite set. It's compact, but has an infinite number of points. So we're not just going to deal with a few individual points. Okay, so we have already shown that this has a unique solution, that Tn of Z equals Z to the n plus dot 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 plus a1z plus a0. And this was back in the first video. Okay, now we're going to make a few little observations about this sequence that we've created. Well, so we have Tm Tn of E. So let's say we found the M polynomial and the N polynomial. Multiplying them together will give some polynomial of degree M plus N, but there's no reason to believe that it is the Chebyshev polynomial. It will be a monic polynomial because we had a leading xcm and x to the n, but it may be that it's larger than the polynomial M plus N. So I'll just state that right here. That is greater than or equal to T M plus N, just by the definition of Chebyshev polynomial. Another fact. T M T N E is less than or equal to T M of E T N of E. Now we'll think about this idea here. For example, let's say we've got these two polynomials here, the first and the second. When we're talking about the TMN, we're looking for a point where the product is small. So we have to pick a single point and find the product between those points. That may not be the best explanation. I'm not happy with that. But I will ask you to intuit the idea here, which is that for this one, we are taking two polynomials, multiplying them together to get some new polynomial. The same is here. And so we have to pick a single point. Whereas here we've got two separate polynomials and we're maximizing them both individually. So it could be larger. The maximum norm of the M polynomial and the maximum norm of the N polynomial, they might not have to be at the same point. So they have sort of more leeway to get larger. So in this case, we're not changing the polynomials here. We're saying this norm is found at some specific z, naught perhaps. Whereas this one, we'd have two separate z1 and z2. And so by giving that freedom to choose, we can make the norm larger. So combining these facts together, we get this Tm plus N is less than or equal to Tmn Tn is less than or equal to Tm Tn. So putting it in the new notation here, we have Tm plus N of E is less than or equal to Tm of E Tn of E. Another equivalent statement is that the log of Tm plus N of E is less than or equal to the sum of the log Tm of E and Tn of E. And then here's where this is unclear to me. Saf's paper says, from which it follows that Tn of E to the 1 over n converges to the infimum k greater than or equal to 1 tk of E to the 1 over k. Now I stared at that and I worked on that for a while and I cannot figure out the it follows here. feels a little like that classic math cartoon. So then a miracle occurs. I'm not sure how to fill that gap. That said, I want to keep some momentum going in these videos. So I am going to just accept that this is true and then move on. And at some point when I figure out why that is, I will attach as a little addendum to this video. But this is our big result here, that the TKs themselves might not converge, depending on the set. On the classical -1 to 1, they do. On other sets, they might not. But what's called the root asymptotics, the asymptotics of the root function, limit of n to infinity of Tn of e to the 1 over n does in fact converge. It exists. And it's equal to the infimum of it, so the greatest lower bound. I feel like that I'm not sure. I don't think that doesn't mean it's monotonically decreasing, but it does mean that, well, there's a subsequence that converges to the greatest lower bound. But anyway, this is defined as the Chebyshev constant. So we've defined a new thing. We have a set. Let's refresh our signs of what this means. We have some set E in the complex plane that's compact. And our first example we were doing in a subset of the real numbers, but that is itself a subset of the complex plane, so that's fine. We then start picking polynomials that minimize the maximum norm. They minimize the error, the distance from 0. And we get a whole sequence of them. We then take the nth roots of each one, and that will give us a finite number, which is what we call the Chebyshev constant. Okay. Now, the point of this is to show that it is, in fact, the same thing as transfinite diameter, which is the same thing as the capacity. That is the fundamental theorem, that these three constants that come from different areas all happen to be the same thing. So we've already seen part of this. We saw this one, I think it was video 3, the one about weak star convergence. We managed to conclude this part. We still need to tie in the Chebyshev constant. So that's what we're going to do for the rest of this video. Okay. So what is next? Well, just sort of by definition, we can say for any monic polynomial P sub n of z, the norm of P sub n over the set E is greater than or equal to the Chebyshev constant to the nth power. Just the way it's defined. The norm of Tn would be exactly equal to the Chebyshev constant to the n. So for any other polynomial, it would be at least that big. Okay. So we're going to do some examples here. Let's do another example on the disk, one of our favorite places to work. All right, so here is a disk, not a unit disk, because the radius is r. Let's write a function g of z is z to the n plus p of z over z to the n, where p of z is n minus 1 degree. So the numerator is a monic polynomial of nth degree. And so that is in the right neighborhood if we're talking about Chebyshev polynomials. All right. So G is analytic for Z greater than or equal to R. It does not have any poles outside the disk. We can see it has a huge pole, or possibly removable, at 0. It's not continuous where Z equals 0. But it is analytic outside there. And that should say norm of Z, excuse me. And G of infinity is 1. You take the limit, the Zn and the Zn dominates, the P becomes negligible at infinity. So the max occurs on the boundary where norm Z equals R. They say out here at infinity, it takes a value of 1. It's analytic on this open domain out here. Open domain is redundant. So therefore, it must have a max on the boundary of that domain, which is the edge of the circle there. So it's sort of the opposite of what you would normally think of. Instead of saying we're at the inside, looking at the boundary from the out, it's we're the outside, and we see the boundary as the inside. It's towards the inside. So the max occurs on the boundary where Z equals R. And since we already established G of infinity as 1, the max must be of G must be greater than or equal to 1. So let's use that fact. The max occurs on the boundary and it's greater than or equal to 1. Okay. Well, that means the norm of Zn plus P Z of E, that's what we're interested in. That's the Chebyshev norm. That is the max where norm Z is equal to R of the absolute value of Z to the N plus P of Z. So we've just established it must occur on the outside there. Now that we could put an R to the N out here. And then inside we will divide by Z to the N, because that is, sorry, I think I might have misspoken a minute ago when I said this is the Chebyshev polynomial. We're using the thing we already know about the maximum principle, that it must be on the boundary. That had nothing to do with the G before. But now we have transformed this, multiplying by R to the N on the outside and dividing by Z to the N on the inside. Since we said norm of Z is R, that's the same thing. Well, we just said that's greater than or equal to R to the N, because all this G is greater than or equal to 1. So what we conclude here is that Z to the N plus P Z E is greater than or equal to R to the N. Now, if P of Z is the zero function, then the norm of Z to the N, or rather, well, yeah, the norm there would just be absolute value of Z to the N. That is this here, this part I'm looking at. Then that would equal R to the N. So see what we're seeing here. No matter what polynomial we pick for P of Z, the norm will be at least R to the N. We have shown that Z to the N gives us exactly R to the N. Therefore, it is the Chebyshev polynomial because it's the one that gets our norm down to that R to the N. So what we are saying then, Z to the N on E is equal to R to the N. That is the minimal polynomial. That is Tn, in fact. So then we take the 1 over n there. The Tn to the 1 over n is R, meaning the Chebyshev norm on E, the unit disk, is R. And we saw in our last video that that is already, we know that is the tau of E and the capacity of E. So our simplest complex analysis example, the disk, is consistent with what we are trying to prove. And historically, that was probably a big motivator. One of these guys, Sego, perhaps saw that, or Fekete, maybe, and decided to do it. Because we've defined Fekete points in a Fekete set. Let's also now define what the Fekete polynomials are. So we got a new type of polynomial that are related to the Chebyshev polynomials. And those are f sub n of z is z minus z1 n times z minus z2 n dot 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 z minus z n of n. So what is this? This is a V, I should say it's V monic. Excuse me, what is this? Go away. Polynomial with zeros on a given Fekete set. I guess when I wasn't sure about the V part, the Fekete set itself is not unique because we saw it's, for instance, rotation invariant. We have the roots of unity, or they could be rotated to other points that are the same distance from each other. But once you define which Fekete set you're using, there's only one monic polynomial that has zeros at all those points. So on the unit disk, the Fekete polynomial, f, that's an n, would just be z to the n minus 1. That's, yeah, that, make that minus a little better looking. Yeah. Why? Well, because if you plug in any of the roots of unity, just by the way roots of unity are defined or created, that they would give you 0. Those are all n of the zeros. And this polynomial is monic. So the Norm, same supremum norm, Fn, in this case would be 2. If I just plug in -1 or I, whichever it is, depending on whether n is odd or even. If n is odd, you can plug in -1 for z, and it'll become -1 minus -1 minus 1 is 2, absolute value. Or if it's even, you plug in I, and so again, you get -1 minus 1. So either way, we can see the largest it gets is 2. Now that's not the same as the Chebyshev norm. If we're on a unit disk, the Chebyshev norm is 1. But if we take Fn e to the 1 over n, that equals 1. So what we just said was that Fekete norm of the Fekete polynomial will always be 2, but if we start taking the roots of 2, getting larger and larger, it'll go to 1. And that is itself, once again, the Chebyshev norm, Chebyshev number. So we get the limit as n to infinity of Fn sub e to the 1 over n is the same as the limit n to infinity of Tn of e to the 1 over n. So the point then is that the Fekete polynomials are not minimal in the same sense that the Chebyshev polynomials are. They might have a larger norm, but they should say limit here as well, excuse me. But they have the same root asymptotics. And the advantage of the Fekete polynomials is that their zeros are always inside E, whereas we saw, back in video 1, if there were gaps in our set, we could have like this, something like that. That would be a possibility where the 0 is inside one of the gaps. But the Fekete polynomials are defined so that their zeros are all inside of E. Okay, so now I think we've laid all the groundwork. We can finally get to the fundamental theorem of classical potential theory. All right, so given we have some E that is a compact subset of C, we have several different things that we can say about it. First off, the capacity is the transfinite diameter is the Chebyshev constant. That's the biggest one probably. Second, the limit n to infinity of Fn of E, the Fekete polynomials, to the 1 over n is the Chebyshev constant, which is also the capacity. So that's what I was just alluding to before, but it's provable that it's true in all cases. And if the capacity is greater than 0, then we know that the equilibrium norm is unique. Equilibrium measure is unique. Sorry, I think measure is what I meant. And that implies 2 more things. So as long as the capacity is positive, there's 2 more pieces that we can say. Let's zoom out. I want this all on one page. The text still eludes me sometimes. Thank you for your patience. All right. C says, infinities. Why? Okay, my computer panicked a bit, but now that we're back, let's say, what were we saying? We were saying if the capacity is positive, then we have some more results. For one, the Theta points have the asymptotic distribution that is the same as the equilibrium measure. So that is useful for practical purposes. We can take a large Theta set and just take the mean of a function at those points, and it is the same as integrating across the entire equilibrium measure, which is generally speaking the boundary. And part D, a little short on space, but I want to fit this on one page. On the unbounded component of C without E. So that is to say that maybe E has a hole in it somewhere. This E is this donut shape. Unbounded component will be the outside part. So on that unbounded component, on that outside part, the limit as n goes to infinity of the absolute value of the Theta polynomials, their norms, or the, sorry, no, not the norms, sorry, the, that limit to the 1 over n at any given point equals the exponential of negative u to the mu e z, and it converges uniformly on compact subsets. So that was a little messy. Let me make sure I understand, or we all understand what's happening here. If you have any point and you start taking the Theta, plug it into the Theta polynomial here at the nth degree, and then take the 1 over n, it's going to converge to the exponential function of the negative potential. Okay, so that's a lot there. And screenshot if you like, because we're going to be jumping around these. I will say parts of this are already done. For instance, part C, our whole thing about weak star convergence already proved this. So we can check this one off right now. We don't need to reprove it. And then once we have C, we can use that to prove D. So let's do that. I'm going to clear the board now. C implies D. Why is that? Well, let's write out what we've got. U to the new Fn of Z is the potential with respect to the counting measure on the Theta set. Well, that's equal to 1 over n times the sum from j equals 1 to n of the log of 1 over z minus zj. So that's just how it's defined. It's the, we evaluate, we're letting z be fixed and the other variable range across the entire set that we're integrating over, which is Fn. Well, by the nature of how logs work, this is the same as 1 over n times the log of the product from j equals 1 to n of 1 over fn of z. Or if you prefer, the negative log of the product from j equals 1 to n of fn of z to the 1 over n power. So that's the value of integral with respect to the nth counting measure on the Fekete set. But we can also say, if we then exponentiate both sides of this, the exponential of this guy up here, if we move the negative over, the exponential of the negative u to the nu of fn would equal just the absolute value of fn of z to the 1 over n. Okay. Now we take the limit of both sides. The left side is constant, so its limit is itself. So therefore, this converges to this. Sorry, that is wrong. Excuse me. Let me restate what I just said. Take limit to n of both sides. We already know this converges to the equilibrium norm, mu e of z. That's part C. Part C says that the new fn converges weak star to the mu e. And the right side, then we just write limit n to infinity fn of z 1 over n. Sorry, I'm a little tired today. I'm stumbling over my words a bit. Ideally, maybe someday I'll remake these more polished. But there it is. We just took the potential with respect to the counting measure and rewrote it and worked it out. It becomes the negative log of the Fekete polynomials to the 1 over n. And then we moved that over and got so knowing C, we want to use it to prove D. So D says that we want to look at the limit of the Fekete polynomials, their norms, their root asymptotics. So we're going to start by saying U, the potential with respect to the counting measure on Fn, that just by definition is we take the arithmetic mean of these first n points, the log, because we're talking about potential, so we just plug it into regular function. So we let, if we're thinking about back to where he said log of z minus t, we're letting t range over all the zj's, and then taking those values, dividing by n. Well, by the nature of logs, we can move that product inside. We can move the sum and turn it into a product. But what is this? The product of all those z minus zj's, that is the Fekete polynomial of degree n. So this becomes 1 over n log of 1 over absolute value of fnz. So we can rearrange that. We can say this 1 over n can move inside, and we can bring a negative out to make that log of fn of z to the 1 over n. Then let's move this negative over to here to the other side. So we'll get negative u to the new fn of z equals log of fn of z 1 over n. And then let's exponentiate both sides. The exponential of negative u nu of fn of z would equal fn of z to the 1 over n. And this is a pointwise thing. But now we can take the limit of both sides here. So now we take the limit of both sides of this. Well, part C, which we've established, says that the limit of the left-hand side would just be the exponential of negative u nu, sorry, not of nu, to the equilibrium norm mu e of z. So that is the limit n to infinity f sub n of z to the 1 over n. So that's part D established. Okay. All right. So what's next? Well, we still need to make the big connection here that tau of E is the same as the Chebyshev of E. And we could have used capacity, but we're going to use it this way because it's going to work out better for us. So let's define a Fekete set. Fn is the set of all zk to the n, where k goes from 1 to n. So we're going to use the deltas again. Delta to the n plus 1. I'm not even going to write of f of n. Technically, the deltas, or of e, the deltas are based on a specific set that we technically should write of e each time, but I'm not going to because I don't feel like it. Now that was the geometric mean. So it was, we had to take n plus 1 points, find the geometric mean and maximize it. That involved taking a root of 2 over n plus 1. So I'm going to raise this to the n plus 1 over 2. That then would just be the max for the zi in E of the product. 1 less than equal to I less than j less than equal to n of zi minus zj. So that power got rid of the root that we would normally have here. Now this is greater than or equal to the product from k equals 1 to n of z minus zk to the n times delta sub n to the n minus 1 over 2. what did I do here? Well, I just peeled off one of the z's. I had this set and the equilibrium here where I had n plus, I had all the points here. That should be n plus 1. I see I just made a mistake there. This is a set of n plus 1 points here is what I had. I'm now saying let's let one of those points vary. So we get all its distances from all the different k points times all the distances of the other n points that we did not remove. Okay, so this is a geometric mean where one of the points is allowed to vary, thus causing it to shrink since it's moving from the maximum. Okay. So now what we do is we will divide those delta n's over to the other side. So I get delta sub n plus 1 to the n plus 1 over 2 divided by delta n to the n minus 1 over 2 is greater than or equal to this. Well, that is the Fekete polynomial at z. It is a Fekete set of n points. Or it's greater than. Greater than or equal to. Yeah, there we go. Yeah, that over there is the Fekete polynomial. It's just the distance between z and all of the zeros, all the Fekete points. Then we can take the nth roots of both sides here. So that will cancel out the n powers on the left. It'll give us delta n plus 1 to the n plus 1 over 2 divided by delta to the n sub n to the n minus 1 over 2. That's greater than or equal to fn of z to the 1 over z, which is itself greater than or equal to the norm of fn. E. I'm making too many mistakes today. Sorry, that should be an n to the 1 over n. Okay, so here we've got this expression with the delta n's and delta n plus 1 on the left. That is greater than or equal to the limit of the Fekete norms asymptotically. So I'm going to separate out the left-hand side here. It's going to become delta n plus 1 over delta n to the n over 2. These both have an n over 2 power times delta n plus 1 to the 1/2 delta n to the 1/2. What did I do there? Well, this negative allowed me to move the delta n to the top. This is positive here, so it stayed on top. Okay. So what do we know about these? Well, right here, we already know that the delta n decreased to 1. So therefore, the numerator is less than the denominator for this piece here. So therefore, this is itself less than or equal to delta n plus 1 to the 1/2 delta n to the 1/2. All right. So that tells us, clear some space here. Where was I? Delta n plus 1 to the 1/2 delta n to the 1/2 is greater than or equal to Fn e to the 1/n. So that's just a chain of inequalities here. This piece is greater than this piece, which is greater than this piece. So we just skip from beginning to end. And that's got to be greater than or equal to the Chebyshev norm. Because we said the Tn's, the Chebyshev norm is the infimum of all the Tn to the 1/n. The Tn to the 1/n are themselves less than or equal to the Fn 1/n. So therefore, these things are going to be greater than or equal to the Chebyshev norm. But now let's take n to infinity on both sides. What is this left side going to give us? It's going to give us square root of delta n plus 1 delta n. As we let n get large, we fill in the boundary of our compact set. At some point, adding more points won't change much, so it's going to be more or less the same as delta n squared or delta n, which we already know converges to tau of e. So tau of e is greater than or equal to the Chebyshev norm. This thing on the left, this sequence here, is greater than or equal to the Chebyshev norm. It converges to tau e, so therefore tau e is also greater than or equal to the Chebyshev norm. And also in here, we see that this thing is trapped between tau e and the Chebyshev norm. So that means once we prove that the tau e and the Chebyshev norm are actually equal, then we will see that the limit here of the Theorem of polynomials is going to be the same thing as well, which is part B of the theorem here. Part B said that those Theceta root asymptotics should go to the Chebyshev norm. Excuse me. We've just shown it's trapped between tau of e and Cheb of e. So once we show they're the same thing, part B will be proven. So really all that's left is the other side of this equality. Tau of e is now greater than or equal to Chebyshev. We now need to show that it is less than or equal to Chebyshev. So let's do that. So this is our goal. We want to show that the Chebyshev norm of E is greater than or equal to the transfinite diameter. Well, if tau of E is 0, that's trivial because Chebyshev norm being based on norms, it's going to be positive or at least non-negative. So let's suppose tau of E is greater than 0. Now Tn of Z exists. Let's define a measure nu of tau Tn is the normalized counting measure. It's like we've been doing, but instead of working with a Theceta set there, it's going to be on the 0 set. So Tn is a polynomial. It has n zeros. We evaluate the function of those n zeros and divide by n. Now, let's use that proposition that we started with, that one about switching the order of the integrals at the potential. It said that the infimum for every z and e of u potential with respect to this new measure we've just defined, because that thing was applied to any measure, it's equal to the infimum of 1 over n log of 1 over Tn of z. But now the infimum of Tn, well, as we defined it, that's just 1 over n log of 1 over little tn of e. And that's less than or equal to the Robin constant. Okay. That was an integral over a measure space. So that gives us negative log of Tn of e to the 1 over n is less than or equal to r of e. I'm just rewriting the left side there, moving stuff inside the log. And then that, taking the exponential of both sides, and again, shifting some stuff around, gives us Tn e to the 1 over n. There's a multiply by negative in here, so we'll flip that to greater than or equal to e to the negative r of e, which is the capacity of e, or tau of e. Oh. Excuse me. So there we go. The Tn of e to the 1 over n is greater than or equal to tau of e. Take this to infinity. That gives, that is by definition the Chebyshev constant. It is itself greater than tau over e. So that does it. Finally, we have completed this. The Chebyshev constant is equal to the transfinite diameter, which is equal to the capacity. So I want to take a moment to sort of sum up everything we've done here. When I started this statement about how these were related just sort of came out of nowhere. And I kind of felt like, well, must be something in some dusty book, and it must probably be hundreds of pages long, and I'll never be able to understand it. So I just have to take it as a given. But no, it took some work. No, not going to deny that. But we got there in a reasonable amount of time. We showed these 3 different constants that were defined in 3 totally different ways turn out to be the same thing. So now I think all the groundwork is laid. I may have to circle back around every now and then, but we've got what we need to really do some work in this thing. And so we're now going to move on to more contemporary research, and soon enough, hopefully, some brand new stuff that no one has seen before, and you'll be here first. All right, so I hope to see you around. Thank you.